Hello, welcome to Maths Decoded. This is the first lecture on mathematical reasoning or logic as we called it in the intro session. So I'll call it mathematical logic today. So this is almost the same as the real life logic, so it will be easy to follow, but it will be a bit more rigorous. Let us define what's a statement first, because statements we use in mathematics, right and left, there are a lot of statements made in daily math. So let us just define what a statement means, and let's get a basic idea of what's happening. So a statement is something. Let me first write down the definition if you're not too bugged about me defining such and such. Statement. A statement is an unambiguous. We know the meaning of unambiguous from a previous video. Unambiguous means not confusing, or the meaning is perfectly clear. The meaning won't change according to your belief or according to the place you live, according to the people you follow. So unambiguous is not confusing. Sentences. So any sentence that is made which will have a truth or false value, which will be true or false regardless of whatever the situation is. So for example, 5 is a multiple of 2. Well, is this a statement? Think about it. 5 is a multiple of 2. It's false. It's not the case that 5 is the multiple of 2. But it's still a statement because it's false no matter where you live, which country you are from, which gender you are, or which god you're believing in. 5 is never a multiple of 2. So this is a statement. It's a false statement that comes later, but this is a statement. So what will not be a statement? What's a non-example? People like mathematics. Some people don't, some people do. It depends on the country you live in. It depends on, okay, I won't go further, but it depends on the person. And this it's to say that this is not a true or a false statement. It's not a true or a false statement. So you cannot put a truth value to this statement. So this is not a statement. This is just a sentence. This one is a statement. So let us see a few more examples of statements. I have a few written down here as examples. New Delhi. This is a very typical example given in all our books. New Delhi is the capital of India. So is this a statement? I'll call this statement, it's a practice in maths to denote all the statements with some symbol. So let us denote this by P. So P says that New Delhi is the capital of India. Well, is P true? First of all, is P a statement? Yes, because either New Delhi can be a capital of India or it cannot be one. So it's either true or false, and we know that it is true for people who have studied a little bit of geography and who know a little bit of our country. So New Delhi is the capital of India. So P is true. True statement. One other example would be, I'll call it by Q, and it will be an object can travel past the speed of light. Is this a statement? I'd throughout my lecture series, I'd encourage you to pause the video, think about what I'm saying, and then come back to the video and continue. So think about this, think about your answer, and then play the video and we'll see. So yes, again yes, Q is a statement because either an object could travel past the speed of light or it can't. No matter what, it will still be a statement. So I'll say that Q is a statement. I'll write a statement with a gap because I'll fill in true or false. So now is it true or is it false? Well, we know that speed of light is the maximum speed something can attain by it's not the lack of our equipment or it's not the lack of human power. It's just a fact that anything cannot go past the speed of light, or else that object would not have existed. That's the talk for a lot of physicists, but I'll just say it's a false statement. If it is so, then that would not have been an object, is what I was trying to say. So this is a false statement, so it's still a statement. So I hope you're getting an idea of what statements mean. So let us look at one more statement, PQR. This is a bit interesting. I have written down all parallelograms are trapeziums. I have heard that people argue about this for quite some time. Well, first of all, is it a statement or not? We'll see whether it's true or false. Pause the video and think about it. So either all parallelograms are trapeziums or they are not. So there are just two possibilities. So this is a statement, and the answer would be either, this is not Q, this is R. The answer would be either true or false. So R is a statement. Is it true or is it false? Whether there is a parallelogram which is not a trapezium. So if I say that all parallelograms are trapeziums, whatever you could think of, are trapeziums, then to say that this statement is false, I have to find a parallelogram, some parallelogram that is not a trapezium. So for that, we need to look at what's the definition of a trapezium. Well, trapezium, the definition says that the opposite sides are parallel. So this is the parallel side. And that's just it. It's a quadrilateral where the opposite sides are parallel. In mathematics, what is written down is what you have to consider. There's nothing such as it is understood or it is said that whatever is in paper is what you have to consider. So in paper, I just have the rule that trapeziums are quadrilaterals which have opposite sides parallel. So this is what makes a trapezium. And parallelograms are quadrilaterals in which the set of both opposite sides are parallel. So I should have said here one of the opposite sides are parallel. So if both the opposite sides are parallel, if this is parallel, then it is also true that one of the sides are parallel because both are parallel. I did not say that two cannot be, So all parallelograms are in fact trapeziums because the rule for trapezium satisfies the rule for defining a parallelogram. So the motto of the video is not talk about parallelograms and trapeziums, but I thought this will be a bit fun for you all. So all parallelograms are trapeziums, so this is a true statement as opposed to what people argue. I don't know why that argument is famous, but that's the case. So these are a few statements we saw, and now let us see a statement, well, let us say yet another one. V is a statement. 5 is an integer or a whole number. This is my new statement or new sentence. We'll have to figure out if it's a statement. I'll get some screen to work with. So let me just go to another screen. Okay, now that we have a new page to work with, let us look at this sentence. 5 is an integer or a whole number. So whether this is a statement or not. So immediately we notice that there's something new going on with this statement, with this sentence I should say. I again and again I'm jumping ahead of everything. So the sentence is actually made up of two sentences. It says that 5 is an integer and the other the sentence is 5 is a whole number. And these two sentences have been linked together with something called OR. So for this whole sentence to be true, what should happen? Whether, first of all, let us see whether it's true or not. Let us forget about this for now. Let us forget about this. And let us just see whether the statement is true or not. So pause the video, think about it again. 5 is an integer or a whole number. So I know that 5 is an integer. So I don't even have to look at the next sentence made. I can already conclude that the whole sentence is true, isn't it? So what did I do just there? I said that if one of the two sentences are true, then the compound sentence, I won't encourage you to learn all these terminologies, but it's the hard truth that some people have to for their exams. So compound sentence, this compound sentence is true if either one of the statements are true. So as soon as I know that 5 is an integer, I'd not even go further. I'd say that this whole sentence is true. So the thing with OR is, when something is connected by OR, so if I say that V, let us name these first. I'll call this A, statement A, or B. So if my statement is A or B, which is also denoted by A, or you can denote it by a V. So this is a symbol. This whole thing could be read as this thing. So this actually comes from a Latin word called vel, which means or in Latin, but this is a symbol quite frequently used for or. So A or B is true if, so is true if A is true. So to say all these things, let me just draw something called a truth table, AB, and the statement A or B. So corresponding to all these, I'd write down what the value of A is, what the value of B is, and what is the value for A or B. So if A is true, B is also true, then A or B according to me should be, so if something is true or something is true. So if either one is true, the condition suffices. So this will obviously be true. If A is true and B is false, which was the case here, then the statement actually holds true. A or B is actually true, because A has happened and B might not have happened. I don't care. if A is false and B is true, even then it means that the statement is true. But if both are false, an example of that would be 5 is a negative number or is less than 0. So that would mean my statement is false because both the sentences are false. So this is called the OR operation, or you can denote it by a capital V, right? So this is a statement again. Take some time to you pause the video, look at whatever we have done, and then you go further. So next on our list is 42 is or I'll not say multiple, is divisible by 5, 6 and 7. And I'll write a proper and. I'm used to writing this short notation, and 7. So this is my statement now. I'll call this statement A for and. Right, this was OR, I called it V, so this is A. Well, is this true? Is 42 divisible by 5, 6 and 7? Pause the video, think about it. So we see that it's not true. 46 is divisible by 6 and 7, but it's not divisible by 5. So the statement made this way, it's not true. So this is a false statement. So A is false, and it's still a statement because it can be true or false. It can just be true or false, not both. So why is it false? Why did it turn out to be false? Notice that this statement is made up of 3 different statements. 42 is divisible by 5. This is one statement, I'll call it A1. A2 will be 42 is divisible by 6, and A3 is 42 is divisible by 7. And all these statements I am linking together with AND. So if I say in one go 42 is divisible by 5 and 42 is divisible by 7 and blah blah blah, you can just write it in short notation this way. So as soon as one of these is false, so this turned out to be false, right? 42 is not divisible by 5. And even though these two are true, the whole statement turned out to be false. So what did we notice? If I just had this, if I did not have this somehow, if I did not have this, 42 is divisible by 6 and 42 is divisible by 7, and if both were true, both are true, so the statement would have been true. But in this case, the statement is false. So what did we see? If we have two statements, say A and B again, and A and B, which can be denoted by other fancy symbol, a downward V. So again I'll get a new page. So A and B can be denoted by this symbol. This just means A and B. So if you are interested, you can Google from where this symbol comes from. So A and B, if both A and B are true, then A and B is of course true, because if I say that Sohail and Mohan went to the movies, if Sohail went to the movie and Mohan went to the movie, then Sohail and Mohan did go to the movie. So and is true if both are true. But if Sohail had gone to the movie and Mohan didn't, then Sohail and Mohan went to the movies is a wrong statement. It's a false statement. Similarly, false and true would give you a false statement, and if both the statements are false, it will be false. So this is the AND operation, and this is all the way they can be linked together. So take your time, understand all these things, and let us meet in the next video, because I think I've been recording for, okay, I think I have crossed my time today. Okay, I'll meet you in the next video. We'll learn about negations of statement, the notion of negating, and we'll also learn about negating statements like these compound statements, so-called compound statements. Okay, thank you then.